yesterday. My power went out yesterday. But no, just not mine. My whole neighborhood. Yeah, the power went out like here, all the way down to San Diego State, and then my neighborhood, and then the next neighborhood over, which is Kensington. So it really was quite a big area that lost their power for a couple hours. Anyway, but that hardly ever happens to me, so let's let it stay that way. So students, yeah, I think there's some, check to see if there's assignments, and I should have checked before. Um, there might be, is there a quiz due today? I put an announcement, I put reminders up for you, but students always check the assignments and it'll tell you the latest due dates, because to be honest, I forget, because I have two different courses and I forget. Um, so, um, so let me just share the screen. So we're going to start talking about, and I probably will bring up like maybe a blank Word file so I can hopefully demonstrate some of this. I have a couple of good YouTube videos that I'll put online for you so you can look at that I think are really, really, it's not required, they're closed captioned. So, but I think this guy did a pretty good job of illustrating what's going on. And they're only like, I like it because it's short. So, okay, so let's see here. So I am going to share the screen and we're going to talk. So we're starting a whole new unit. So we did do like a one brief topic on searching, that was binary search. And okay, and then we did some other stuff with like the big O notation and complexity and a little bit of recursion. And so now we're going to talk about all the classic sorting routines. Selection, insertion, shell sort, and then the two real famous ones, like the most famous sorting algorithms in the sorting world. Yeah, quick sort and merge sort. And then there's something else called heap sort, which maybe I think I'm supposed to talk about that. Though it's not. It's merge sort and quick sort are the two big ones. Okay, so I'm actually going to share this with you. So again, I actually put a PDF version of this up, and hopefully. So you should see something right now that says Math 140, Introduction to Sorting. And so in the slides, and actually, if you actually read in the Zai book, they're talking about sorting lists, like arrays of integers or a collection of integers, or like a list of integers. But this can easily be extended to arrays of objects. And I'm going to just show you. It's really because if you have the comparable interface, so if a class implements comparable, you can compare two objects from that class. And that means you can sort a collection of objects from that class. So we'll talk about that. It's only minor changes to the code. Okay, so let's just go on here. And Math 140, Introduction to Sorting. Okay, so we're hopefully today, we're going to just talk about these two really fun algorithms, selection sort and insertion sort. And they're really not, they're classic algorithms. Like if you were like at a computer science party, like if you went like on a computer science cruise, you know, people would probably expect you to know what selection and insertion sort is. Yeah, they'll be talking, hey, that guy over there doesn't know insertion sort, can you believe it? But anyway, but they're really, but they're really not widely used. They're only really good for small arrays. And then for like big lists, we use quick sort and then merge sort. And we'll see where insertion sort kind of comes into play a little bit in a quick sort, and I'll talk about that probably next week. Okay, so the thing about it, selection sort. So I see where I say there it sorts in place. So meaning it changes the array, right? So we're not making a copy of the array. So it's not like we have the original array and then make a copy of it so they're in two different memory locations, and then we sort so that we have then the original version and then the sorted version. So when you use it, so when you execute the selection sort algorithm on an array, you're permanently changing the order of the elements. And when you're done, everything will be in sorted order. So if for some reason you actually needed the original order, you'd have to make a copy first. And hopefully, I think I have a way of maybe illustrating this because I don't actually have a whiteboard right now. But so just think of it like an array, which is like a horizontal list. And so it's selections both. I like the way the book kind of thinks of this because the previous book I used didn't do this. Selection sort it's going to divide, so it's an iterative algorithm. So if it's an array of length 10, it's going to take, first of all, students, let's say you have an array of length 1. It's sorted, right? There's nothing to do, okay? And so if you have an array of length 2, well, you want it in ascending order, like the element 0 is the smallest and element 1 the biggest. Let's say it's an array of size 2. Well, it's just one comparison. So basically the number of, the number of iterations to sort an array with these two algorithms is if the length is n, it's n minus 1. So once again, if the length is just 1, it's 0 iterations, right? It's sorted. So the number of iterations to sort for both of these algorithms is n minus 1, where n is the length of the array. But it's an iterative algorithm. And so at every step of the algorithm, we're just gradually building up this sorted list. Okay, and so, so let's just start with selection sort. And what selection sort does, it scans the whole array and finds the absolute smallest. It finds the, like if you're taking calculus, what would they call that? Not the local, the absolute minimum. It finds the absolute minimum and puts it in position 0. And it actually swaps. So let's say the absolute minimum is, let's say, at position 10. So let's assume the absolute minimum is at position 10. You exchange what's in position 0 and position 10. And when you're done, you're guaranteed what's in position 0 is the absolute minimum. And then you don't even have to worry about position 0 anymore, because you know that has the minimum. So now you just consider values from 1 to the end of the array. And then you find the next absolute minimum and put that in position 1. And so it's a very intuitive algorithm, very kind of a simple, both these algorithms are really very simple. But selection sort is always looking for the next absolute minimum. Okay, and so what this algorithm does, so it's dividing our array up into 2 parts. There's a sorted part, and that's it's on the left. Not necessarily, so the left side is sorted, and the right side is not sorted. So the left side might be, every iteration, the left side, the sorted part's getting bigger and bigger and bigger. So every iteration we're sorting, the sorted part of the array is growing. So by the time you're done, the whole thing is sorted. Okay, so then I is going to denote the left boundary of the unsorted part. So basically it's the smallest index of the unsorted part. And everything to the left of I is sorted in ascending order. And we can actually change the code so it's descending, but that's nothing we really need to worry about. Okay, so the sorted part are the absolute smallest parts of the array. And so let me just go through this code a little, and then maybe if I get into a Word file, I can demonstrate. Or maybe I'll go into the worksheet. I have a worksheet for us, so let's go in the worksheet. I'll demonstrate. Okay, so because visuals I think are better than just kind of talking. Okay, so let's just say, so since, and again, anytime you have a question, just call out. So again, we're doing selection sort. And selection sort is always looking for the next absolute minimum. So look at this, that array called numbers. And if you look, 9, 11, and 17 are the absolute smallest values in the array. If not, then I made a mistake. Okay. Do you agree with me? 9, and I'm assuming you're all shaking. Yeah, that's right. You're all shaking your head. Yes, I guess. Okay. Because unless I made a glaring error, which is always, believe me, students, I've made a lot of those. Okay, so 9, 11, and 17 are the 3 absolute smallest values in that array. Okay, and so everything, okay, so I is the left boundary. So what I'm saying here is that, let's see if from here, maybe I can put an absolute value. Is everything to the right of that bar I just put in, so that part is unsorted. Everything to the left of the bar is sorted, 9, 11, 17. That's sorted in ascending order. And then everything to the right, well, it's not sorted. 100, well, 24 is less than 100, and then 19 is less than 24, and it's going in descending. Oh, then we go up to 36. It's a mess. Okay, where the left side is really this it's just so peaceful because it's all sorted. Okay, so anyway, okay. So the values in positions 1, 2, and 3 are sorted, and it's the absolute smallest values in the array. Okay, and values in positions 3 above are not sorted. So our goal now in life, students, is let's find the absolute smallest in this unsorted part here. So we're going to find it. So we're just going to look at this part here that I'm kind of. So we're going to scan the array, using like a for loop, and starting from position 3. We're going to start from position 3 and go all the way to the end to make sure we get the absolute smallest. Because if you don't look at all 4 of those elements, you don't know that you've gotten the absolute smallest. So you actually have to look at all 4 of them. Okay, and we see, of course, it's, it's going to be 9. We see it's 19, but the computer one by one looks at them. Okay, and so then what would happen next is, and we'll see, hopefully, I'm trying to remember what happened on the next page. So once we discover that the next smallest is at position 5, which is the 19, we would exchange the values at index 3 and element in index 5. So let's just, I'm looking forward to what's happening. It's a cliffhanger here. Okay, so anyway, yeah, so at step I, selection sort scans elements I through numbers length -1, goes all the way to the end. And it finds the index where we can find the smallest remaining value. And I'm calling it index small. So here in the previous slide, the index smallest would be 5. That's the location of the smallest. I think that's what they call it in the book. Okay, and then we exchange numbers of I and numbers index smallest. And then you increment by I, meaning, oh, we're ready to get the next smallest. Okay, so see what happened after you did the exchange? See now, remember, see that was this is the original list at I = 3, right here. That's the original list. See, we got this big mess right here. It's like, and you just kind of want to avert your eyes. Why can't I do this now? Now that's strange. Oh, yeah, so this, yeah, I see what I did, okay. So this right side here is unsorted. It's like, yeah, so it's, yeah, so, okay. And so we're trying to clean things up here. We see that element 5 is the small. So then we exchange element I is 3, smallest index is 5. So we exchange what's at position I and position index smallest. And this is what we get here, right? So now you see how the 19, and then we increment I by 1, and I is 4. So now it says this part. It's this part. It's the last 3 now that are unsorted. And now the first 4 are sorted. So that one iteration, see, every iteration, we're just building up this sorted list. And we're looking for the absolute smallest of what's remaining. So it's very intuitive. It's a very simple algorithm. I'm not sure who developed it. But it's really kind of a trivial algorithm in a way. So, okay, let's see what else I want to say about this. And then maybe we'll do a couple of worksheet problems and then maybe even look at the code. Okay, oh, so yeah, so here I have a more complete example here. So, okay, so, and students, what I've done here is in red, I've highlighted the elements that have been exchanged. And hopefully I didn't make, if I made a mistake, then I'll correct it. Okay, and so when I say exchange 2 and 10, I'm talking about the numbers. I'm not talking about the position numbers. So basically we exchange what's at position 0 and position 1. Okay, so here's our original array, and so now we're gonna, so our I starts out at 0, and then we're gonna scan the rest of the array. Okay, so yeah, so if we just look at that, one element alone, 10, it's sorted. So we're gonna actually look for the rest of go through the rest of the array and see if there's anything smaller than 10. So we look through all of this stuff right here. I'll just highlight that temporarily first. Oh, what happened here? Yeah, so the very first iteration, yeah, we scan that part of the array, right? So we scan all those elements I now haven't, maybe I shouldn't keep doing red, it's getting confusing. Or maybe tell you, I'm gonna go back here. I know I've got an idea. So what we're gonna do is, in the very first iteration, we're gonna scan all the values to the right of that bar I just put in. And we're gonna find the absolute smallest. And the absolute smallest is 2. Now, of course, that's the advantage we have over the computer. We can just look at it. Where the computer has to go 1 by 1, there's actually a for loop. We'll look at the code in a second. And the book has pseudocode. Actually, I implemented the code for us. Okay, so where are we? Okay, yeah. So we scan that Okay, so we see index smallest is position 1. Okay, so you exchange the 2 and the 10. And now, okay, so now we're guaranteed what's at that very first position is sorted. Okay, so now we're going to scan. So the first iteration we exchange the 2 and the 10, and then what's going to happen is the next go round. Let's do one more because I don't want to get too confusing. Okay, so we know that so now we want the next smallest. So we're going to see, is there anything smaller than 10? Is there any value that's smaller than 10? And so we scan and we look for the absolute smallest. We see that it's 4. Is that right? Yeah, we see that it's 4. So we scan for the absolute smallest and see, oh, well, 4 is less than 10. And so we exchange the 4 and the 10. Okay, so now, you're guaranteed, so after the second iteration, you're guaranteed that 2 and 4 are the absolute smallest. Okay, so then, I is 2. And so we want to see, is there anything smaller than 78? So we scan the rest. Oh, we see it's 7. So we exchange 7 and 78, right? So iteration 3, you're guaranteed that the first 3 are small. So in every iteration, you're gradually building up this sorted list. And so the one thing is, so at the end of the first iteration, the first one is, you can kind of stair step. At the end of the first iteration, the leftmost element is the smallest, and then it's the 2 absolute smallest, and then at the end of the third iteration, it's the 3 absolute smallest. And so then in the fourth iteration, of course, it's the 4 absolute smallest values. So by the time we're done, it's sorted. See, so this last one here, for this last one, so we want to say, was there anything less than 78? Well, 45 is. So you exchange the 45 and the 78, but then there's only one element left, and it's got to be the absolute largest. So this array is size 8, but it takes 7 iterations, right? Because after you find the first 7 smallest values, there's only one element left that has to be the largest. So maybe, let me see what's on the next slide. Maybe let's just look at the code and then, okay, so let's get back to this in a second. So we just have to, so it's a very simple algorithm, and let's just look at the code, and and then maybe we'll do an example here. So I'm going to share the screen. And students, also just remember, anytime you want to leave, I encourage you to stay, but I don't take attendance, and just stay as long as it's serving your purposes. You don't hurt my feelings. My feelings aren't going to be hurt if you leave. I'm not actually noticing. Except, I see some of the names. I don't know, I don't see all the names. But anyway, I guess I get so excited about talking material, sometimes I forget to look at the names. Okay, anyway. So but any questions, just shout out or chat or something. I don't think anyone's chatted. So I'm going to stop sharing now, and I'm going to go to the PowerPoint, the Eclipse. Yeah, I'm going to open up Eclipse. So stop sharing. Okay, so I'm going to open Eclipse. So I'm going to share Eclipse, and I'm just going to show you. And I put these files. I haven't created the module yet, but remember, there's under Files, there's that folder called Lecture 10. Eclipse is right here. Okay, so then this bar gets in my way. Okay, so let's just look at selection sort for int, you don't necessarily. Okay, so what I put some extra stuff in here, students, just to kind of demonstrate what was going on. Like all those print statements. Like, do you see on lines 33 through 35, I have a bunch of print statements just so we can kind of see what's going on. Okay, but basically this I'm not sure if this is getting in the way, this bar here. Okay, so let me see here. Students, let me just. And what's this? Okay, so I'm going to close something. Hopefully, I'm not closing the. If I leave the room, I'll come right back. Okay, so no. Okay, so I'm still here. Okay. Okay, so we have this loop right here. So again, selection sort. It's a nested loop, right? And so and so we iterate. So if you see that outer loop that starts at 19, we're going to iterate from 0 to, instead of I less than numbers dot length, it's I less than numbers length minus 1. So if the length is 10, we actually do 9 iterations. So the number of iterations for both algorithms is always 1 less than the length, because when there's only one value left, then it's guaranteed to be sorted. So we assume, so let's just find the absolute smallest. So you assume that the absolute smallest is at position I. So when I is 0, we're looking for the absolute smallest. So when I is 0, we're going to scan that whole array, look for the absolute smallest, and then put that in position, and then exchange 0 and whatever an index smallest happens to be. Okay, so we set index, so I is 0, we initialize index smallest to be I, so initially index smallest is 0, and then we scan so then this inner for loop scans all the values to the right of I for the absolute smallest, and that's basically your classic, let's find the smallest value. Okay, and so all we're doing is comparing numbers of j. We're seeing is numbers j less than numbers of index smallest. If it is, we update the index that has the smallest. We don't actually care what the smallest is. All we care about is its location. And when you're done with that inner loop, now we know we're going to exchange I and index smallest. Now I added a few things there, students. We're going to run this in a second. Just so hopefully this kind of illustrates what's actually going on here, maybe not. But the important thing is here, so after you're done, so now after you're outside the inner loop, then you actually, here's some code to actually do the exchange. You save numbers I, so right now I is 0. So when you do the exchange, you have to save what's in, let's say numbers of I, because we're going to assign, in line 39, we assign numbers of I a new value. So let's save what's in numbers of I is right now 0. So we save that in temp. We update numbers of I we set it to numbers of index smallest. And then we set numbers of index smallest to temp, which is that value, which is the former numbers of I. So you swap what's in numbers of I and numbers of index smallest. And then I have some extra, all this kind of calling. Now we're going to display the array, print the current state of the array. Okay, but basically, if you're going to take this code and you want it to make it like this real production code, you just take out anything, you take out anything that prints values. So since why don't we actually, let's see if we can run this, and let's see if hopefully the output kind of illustrates what's going on, maybe not. So we have this kind of simple array on line 51, and so I have a method that it'll print out the array, and then we're going to call selection sort. Selection sort actually sorts in place. So after you call selection sort in line 55, the array is changed. It's the same numbers, it's just the order is changed. Element 0 will be store 2. And then after that, a 4. Okay, so then, so let's just try this and let's see what happens. Let's see what happens. We've got, how many elements in that? 4, 8. So it should be 7 iterations. Hopefully it's not too much output. Can we see the output window? Maybe I need to, oh, here we go. Okay, so there we see the original array. Okay, so yeah, hopefully these statements help a lot. So like the first block, find smallest value for indices greater than or equal to 0. Smallest value is 2 at position 1. You exchange 0 and 1. And then, so you can see that's what happens. So the original array is 10 to, you can read it, 10 to 78, way there at the top. And then after the first iteration, yeah, we exchange the 2 and the 10. And it tells you what's actually being exchanged at each time. So I don't need to read it. It'd probably be easier for you to read this yourself. But, and I just wanted to say one other thing. So are there any questions about this? And so I'll let you run this yourself. And then you can actually, here, I'm gonna go back to here. And then you can actually go into the main method and just put all your favorite numbers in there. You probably have a collection of like 10 of your favorite integers that you can put in there. Okay. I just wanted to show you, the book only has this algorithm for integers. So the algorithm, if you notice, so when you sort, we have to be able to compare two values. And so with integers, you compare with greater than, Well, here we're using less than in line 28, right? That's how we compare if some number is less than another number. Okay, so it's easy to convert this to an array of type objects, and I'm going to use that comparable interface. And I'm not using the generics. I'm going to get a warning. The code has the code is trusting that my array is going to be all the same type of objects. Okay, so okay here. But look, so wherever we see less than, we're going to just exchange it. Remember, how do we compare two objects? Well, we have our friend, the comparable interface, and it defines a method called compare to. And so if you look at that selection sort, okay, so they're in that line 28, we're going to change that to compare to, and they're on line 13. So temp is actually a value, and see, it's an array of type int. So yeah, so temp is actually a value that we use that for exchanging values. So now let's just take a look. So I have this it's almost identical code. Selection sort for comparable. And so if you look in the main method, I can now sort an array of type strings. I mean, it's the exact same algorithm, but the code is just slightly different. For two, we cannot compare strings with the greater than or less than operator. So we need to use the compare to method. So, okay, and so that's why if you look at this code, if I can scroll, I'm not sure if I can scroll to the top. Yeah. What it's doing is taking an array of type comparable, which means that every element of that array, remember what is comparable? It's an interface that defines a method called compare to. And so what it means, so in line 13, when the parameter type, it's array, we know it's an array because it's got the square brackets. So it's an array of type comparable. It means every element of that array has a compare to method. That's all we know. And the thing is, students, theoretically, ARR could be objects from different classes, as long as the class implements compare to, like that's for that assignment we just finished. Just think, we wrote a class called student that implemented compare to. We implemented a class called university course that implemented compare to. So theoretically, one of those objects could be in line 13 of that array ARR. One of them could be a string object. One of them could be like the student object from the assignment we just completed. And another one of them could be a university course object from the assignment we just completed. And so that's why we get a warning that we're not, because I'm not using generics, just to make it simpler. Okay, so we just have to, now we're just using this for test purposes. It's not real production code, so that's fine. We just have to make sure and that all our objects are the same type, which they are. Right, so I'm testing this on an array of 56. They're all strings. So the computer just has to trust that everything that we're passing to this ARR array on line 13, they're all objects from the exact same class. Okay, but I think that's what it's doing with it. Yeah, comparable is raw type, meaning we're not using the generic. And it's saying, yeah, so you should be using the generic. That's what they're saying. Okay. Okay, but if if this is if someone was paying us like a lot of money, we do that. Okay, but no one's paying us. Okay, so a lot of money anyway. Okay, I guess I'm getting paid. I mean millions. Someone's got to pay us like really big money to implement that with the generics. Okay, so students, it's the exact same code. Here's the one. There's only two real differences. Remember, you can get rid of everything. You can get rid of anything with the print statements. That's really not part of the algorithm. But So we need this temp for swapping. Okay, so we're going to save an element of the array in temp. And so the array is of type comparable. So temp is of type comparable. That's one change. And do you remember we had that less than in line? We're comparing ARR of J and ARR of index smalls with the less than operator. Well, now we have to use the compare to method. So if you look at my comments, if ARR of J is less than ARR index smallest, if you wrote that, you get a compiler error. If you want to check if one object is smaller than the other, you have to say ARR of J dot compare to, and then inside the parentheses ARR index smallest. That's going to return an integer, and if it's negative, then the calling object ARR of J is smaller than the argument. Okay, so it's really not that much harder, but if you're taking a test, and now since this won't be on your test, But I mean, when I would proctor in class, yeah, I'd put this on the test, and about half the class would get it. Okay, so, but yeah, let's just run this for fun. And there, oh, students, and then we have a real treat coming up. Insertion sort, okay. It's kind of a variation on this. Or we have to, okay, so let's see, let's just, okay, I'll try to pick up the lecture. Okay, so students, first of all, what are we trying to sort here? That list is strings. And remember, strings are sorted in alphabetical order, the way they would appear in the dictionary. And they're all the same case. If the cases were different, some were uppercase, some were lowercase, then it would be different. Because in fact, the uppercase would be less than the lowercase. So that's the one oddity about Java, is that uppercase characters are considered to be smaller than lowercase characters. It's not just Java, it's just computer science. All of computer science. Maybe somebody wasn't paying attention when they made that rule. So a year later, what did you do here? Oh, it's too late now. The whole world thinks that lowercase a is greater than uppercase a. Okay, so anyway, let's see here. Okay, so I'm going to run this application. Now, again, we're going to do the exact same thing. And by the time we're done, our array is sorted, right? AA, ant, ants, because, cat, follow, rain, 7, zebra. And, but if you see here at the very first iteration, so can we see the original array? Yeah. So here's the original array way at the top. And the absolute smallest string is AA. And at the end of the first iteration, we're exchanging AA and cat. So after you're done with the first iteration, you know it's at position 0 is the absolute smallest. And then you just have to search, and now you just have to find the next smallest and put that at where the zebra is right now. So it's the exact same algorithm. You know, the algorithm is the same. Implementing is just slightly different. So any questions on that, students? And I'm going to stop sharing this. I think we won't do the worksheet right now. Maybe let me talk about insertion, and then maybe we'll do 2 worksheet problems. And then at the beginning of the next lecture, I'll talk about the worksheet. Okay, so, okay, so students, let's just go back to if there are no questions here, let's go back to the PowerPoint slides. And let's just talk briefly about runtime. Okay, so let's just move on here. We'll finish with that. Whoop, 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 whoop. Okay, so I think there's 1 or 2 slides I missed. Okay, so let's say n is the array length. Let's say n is the array length. So, okay, so selection sort uses about n squared over 2 compare operations and n minus 1 exchanges. So so there's actually an exchange done at the end of, so remember it's a nested loop. At the end of the inner loop finds the absolute smallest and exchanges that absolute smallest with what's currently at position I. And then at the end of the inner loop, we do an exchange. So you're guaranteed that for every iteration, there's n minus 1 iterations, and you're guaranteed there's exactly 1 exchange. Now, what's happening in the inner loop? The inner loop is actually doing comparisons, right? Because remember, we're scanning okay, so let's say we're trying to find let's say I is 0, and we're trying to find the absolute smallest. So what we scan from I so we scan from j equals 1 to j equals n minus 1. So to find the absolute smallest, we do n minus 1 comparisons. Okay, so we assume the first one is with that position 0 is the smallest, and then we scan the rest of the array to see if there's anything smaller. That's n minus 1 comparisons. Okay, so then for the second iteration, okay, we assume that what's at position I is the second smallest, and we scan the rest of the array, and it's n minus 2 comparisons. And if you've taken calculus, what you see is the number of comparisons turns out, this is not something you need to memorize. It's a good formula. I mean, if you're going to go on computer science, that the number of comparisons is 1 plus 2 plus 3 because there's n minus 1 iterations all the way up through n minus 1. And what that turns out to be is, there's actually a closed form formula for that, which you'll learn in first semester calculus if you haven't taken it already. And it's n minus 1 times n divided by 2. And if you multiply that out, you get n squared minus n over 2. And remember that big O estimate? We drop the lowest order terms, we drop any coefficients. All we care about is the highest order term. So there's about n squared number of comparisons. So there's about n minus 1 exchanges, and the big O estimate for comparisons is n squared. Okay, so n squared is the dominant term. N squared is the dominant term. So it grows. So this algorithm grows like n squared, where n is the size of the data size. Okay, so let's say the array size is doubled, then the number of operations goes by a factor of 4. So like an array size of 2n requires about the quantity 2n squared, which is 4 times n squared operations. So if an array of size n requires n squared operations, an array of size 2n requires 4n squared operations. So you double the data size, the number of operations grows like a factor of 4, which isn't great, but it's, it could be worse. So, and then I think I have made an interesting observation on this slide here. So the one thing about selection sort, let's say the absolute smallest. So remember what it does. So we start off the algorithm by, we're going to look for the absolute smallest value in the array and place it in position 0. Let's say position 0 is the absolute smallest. Let's say position 0 is, it has the absolute smallest value. We still do the exchange. An exchange is still always done at the end of every inner loop. So if the smallest value for iteration I is located in index I, yeah, you actually exchange AR of I and AR of I. And I'm not sure if, and I've seen a few implementations of this algorithm, and I've never seen like some kind of if statements in there. Oh, if these are equal, don't do anything. Maybe doing the exchange it's not really that efficient to put like if statements in to check to see if the exchange is unnecessary. So because it's only a few operations. What is it, like 3 operations? You store what's in position I, you exchange what's in position smallest and position I, and then you update position of index smallest. Okay. So students, any questions on selection sort before we do our next fun algorithm? Insertion sort. Now I think of the two, insertion sort is actually the more, I'm not sure actually anyone uses selection sort. Insertion sort for small arrays. If you're going to sort a small array, I think you'd be more likely to use insertion sort than selection sort. In fact, I think one of the teachers told me he doesn't teach selection sort, but I like it. It's like one of my favorite algorithms. Anyway, so I teach it. Okay. So then here I'm telling you where the code is. Yeah, if you want to look at the pseudocode, you can go look in the Xi book. Okay. And then if you want to look at the real code, you look at the files I put in line. But basically, I just took the code and I added some Java. I filled all the blanks in. So now students, the famous insertion sort algorithm. Okay, so here it's kind of a variation of it's different than the old algorithm. Again, once again, the array is going to be divided into 2 parts, a sorted part and an unsorted part. But the sorted part is not going to have the absolute smallest values. Basically, they're going to be like local minimum, versus a global minimum. So once again, but let I denote the left boundary of the unsorted part. Okay, and so everything to the left of I is sorted. So again, it's an iterative algorithm. So at the beginning of iteration I, everything to the left of I is sorted in sorted order, where everything to the I and above may be unsorted. It's like, yeah, total mess. Okay, so anyways. Okay, so yeah, so the value, I was reading that just to make sure, I thought I made a mistake for a second. No, I didn't. Okay, so the values to the left of index I are sorted, they're in ascending order. That's how both of these algorithms sort. They sort from smallest to largest. And so in this case, instead of being the absolute smallest in the array, they're the smallest values in positions that were originally in position 0 through I minus 1. So there's no swapping. We're not like swapping, oh, let's swap position 0 and position 9. So basically, it's more like a local minimum, where selection sort is always looking for a global minimum. And so the code's a little bit more tricky. I actually think it's really good. If you're a computer science major, I really encourage you to understand this code, not because it's so exciting, just because, well, you have to be able to read code. So I think it's a useful exercise. Okay, so here I just have pseudocode. Okay, so and so what it does, it's going to put position I in its proper. So let's just assume everything from position 0 to I minus 1 are sorted in ascending order. And now what we're going to do is we're going to put the element of position I in its proper place just by shifting to the left. We're not going to look to the right. Like in the other selections, so we kept looking to the right of position I for the next absolute small. So now we're just going to, it's kind of like you're playing cards. I'm not sure it's a good analogy. Like maybe your cards are sorted and then you have a new card. Every time you get a new card, you put it in its proper place. We're doing that. So we're taking the value at position I and putting it in its proper place. Okay, so we set J equal to I, right? So that's pseudocode. And now we're just going to keep looking to the left. And if A sub R, and let's say the name of the array is A R, like R, I guess I called it. Let's say R is less than, let's say ARR of J is less than ARR of J minus 1. That's the element immediately to the left. We exchange and decrease J by 1. So we're going to take this value stored at ARR of I and just gradually move it to the left until what's to the left is actually less than ARR of this new candidate. We're trying to put it in its proper place. So let's just look at an example, because the code can be kind of hard until you see an example, and I can't see because I have this in my way. Okay, so once again, okay, we're going to let I equal to 3. And if you can see here, students, I'm going to put that bar in again. Those first 3 values are sorted 1, 5, and 7. And I want to now let's put the 2 in its proper place. So we're going to put so again, we're only going to look to the left. We don't care. So as far as we're concerned right now, I is 3, and anything to the right, unlike the previous algorithm, anything to the right of 3, we don't care about. Okay, so we're going to look to the left, and we're going to put that 2 in its proper place. So let me see what I have there in the next slide. Okay, hopefully it's in a mess. So J is 3. So ARR of 3, which is 2, is less than ARR of 2, right? Because 2 is less than, what, 7, right? So exchange, what's in position 3 and position 2. And now the new array is 1, 5, 2, 7, and then everything to the left of position 3. Okay, but we keep going. We keep looking to the left until we can't do an exchange anymore, until we can't do a valid exchange anymore. That means the element to the left is greater than or equal to 2, or we're at the end and there's no more elements left. Okay, so remember we're trying to put position 3, I equal to 3 in its proper place. So we set J equal to I, so J is equal to 3. J is set to 3. And then we compare position 3 and position 2. Position 3, what's at position 3 is smaller than what's at position 2, so we do an exchange. Now we decrement J by 1. Now J is 2. And now we compare, we have to look at don't look at the original array, you look at the updated array. And now you compare, is position 2, what's at position 2 less than what's at position 1? So in other words, it's 2 less than 5. And the answer is, 2 less than 5. That would make sense. And it's true. 2 is less than 5. So now we exchange AR of 2 and AR of 1. So the 5 is now to the left side of 2. And then now, okay, so then we're done with so we did this second iteration, and now we have to see. We have to compare 2 what's at position 1 and position 0. So we decrement J by 1. And basically, you compare, what you do is you compare ARR of I. Basically, what you're doing is you're going to compare is 2 less than 1? And the answer is no. Right, so you stop doing the exchanges. And the thing is, when we put 2 in its proper place, we've already made sure that 1, 5, and 7 are already sorted. So if 2 is greater than 1, then 2 has to be bigger than everything to the left of 1. So that's insertion sort. So then the next round, you'd put 99 in its proper place just by looking to the left. Of course, the first thing you would see is that 99 is less than 7 is false. So, you would just move on to 11. So here I have this really great slide here. Okay, so here is our example here. So we just start off with that array, 10, 2, I made it kind of small, 10, 2, 78, 4, 45, and 1. So it's a total mess, it's not sorted. Now students, when we start this insertion sort process, and I'm not sure I actually put this emphasize this in the slides enough or emphasize it all. We always start at position 1. So the first element we're going to try to put in its proper place is that element that's at position 1. Because if the array is just of size 1, if we say, well, let's put 10 in its proper place, well, if the array is just of size 1, well, 10 is automatically sorted. So the idea is basically in the first iteration, we're going to sort 10 and 2. And see how, in the part that's highlighted in red, see how that's sorted? And then in the next iteration, and you're not going to show all the individual exchanges. And like even in my class, I don't show, I mean, the in-person classes, I don't ask them to do all the exchanges. I just show them what's the end result. Okay, so after the outer loop of iteration 2 of insertion sort, the first 3 are sorted. And in this case, there would be no exchanges because 78 is greater than 10. Okay, so then in the next iteration, we're going to put the 4 in its proper place. We're going to put that 4 in its proper place. And then, so to actually write it out, it's really not that hard, right? You just make sure the first 2 are sorted. And then the first 3. And then when I is 3, we make sure, then after I is 3, we make sure the first 4 are sorted. And then the first 5. And then the very last iteration, you just make sure the whole array is sorted. So actually writing out an answer, even if you didn't know the code, I could probably do this, I think to a reasonably intelligent, maybe like someone with no, I was going to say high school student, but maybe I shouldn't say that. I think a reasonably intelligent person who had no computer science background. I could say, okay, let's just do, here's an algorithm to sort an array. Sort the first 2, then the first 3, and then the first 4, and then the first 5, and then the first 6, all the way up to the end. That's insertion sort. And basically, there's always a global minimum, right? So there could be, notice one thing, students. Let's say like the end of iteration 3. See this one right here, the one where the first 4 are sorted. The smallest one, it's not the 4 smallest ones in the array, because there's a 1 out there. 1 is there way at the end. And we don't put that into its proper place until the very last iteration. So insertion sort just has a local minimum. Where insertion sort just has local minimums, where selection sort, you're always looking for the absolute smallest in each iteration. So let's see, is there anything else? Let's see what's on the next. Any questions? I think let's see here. I think it's just these 2 slides left. Okay, so since let's just quickly look at the code for insertion sort, and then maybe we'll look at these slides and I'll ask some questions. It's kind of a lot, it's almost an hour already. Normally in class, again, if we were teaching on campus, I would not lecture this long. I would lecture and then people we'd do problems in class and we'd go back and forth. Okay, so I'm going to stop sharing this. And let's go back. I just want to show you, I did implement this code, but I have to share the screen, I guess. It's a prerequisite, which I have. I'm really bad at doing that. So, okay, so insertion sort, and this is the one, and I won't show you the other one because it's basically the same trick. All I'm doing is taking the insertion sort for int is sorting, it sorts for array of integers. And then I also have insertion sort for comparable. Basically allows us to assert arrays of objects where the underlying object has implemented comparable. And so here we actually start at I equal to 1, because if the array, if let's say I is 0, then our array is going to be of size, then we're only considering the array of position 0. An array of size 1 is automatically sorted. So when I is 1, what that means is that when we're done with iteration, whenever we're done with iteration I, that means that everything up through, all the elements from 0 through I are sorted. So when I is 1, when we're done with iteration 1, the first 2 will be sorted. And when I is 2, it'll be the first 3 that are sorted. Okay, so, and so forth. I have a bunch of comments in there. And so we start, and that's all it is. We start I out at 1, and I think that line 18 is really just for my output purposes. That's not really part of the algorithm. And then we have that, it's this, of all the things we've done today, it's that inner loop that's starting on line 40. I think it's probably the most complex code. Maybe it's the most complex code we've seen so far in the whole course. I'm not saying it's complex, I'm just saying so far in the course, relative to what we've seen. And I really encourage everybody to try to understand this. If you think computer science is something that interests you, definitely you want to be able to understand that. So remember, what we're doing is we're putting the element at position I in its proper place by looking to the left. So we set j to I. So let's say I is 10. Okay, so we want to put the element stored at index 10 in its proper places by doing comparisons to the left. So you said j equal to 10. And then all you were doing here is numbers of j less than numbers of j minus 1. If that's true, that means that numbers of j is less than its neighbor to the left, and you do an exchange. But we also have to make sure j is greater than 0, because we can't check 1 to the left. Right? If j is 0, we can't go numbers of j minus 1. So you want to make sure when you look to the left, your 1 or the index j is 1 or greater. And then if that's true, then so then you just do the exchange. So you just do the exchange, right? So let's just try to run this. Let's see how I did it. That's how we're doing. Okay, so there's our array, totally unsorted, 10, 2, 78, blah, blah, blah. Okay, and so once again, students, the array is going to be gradually built up. So after the very first, see, it says after inserting 2 in its proper place, positions, I'm not sure if that's getting in the way, this zoomed thing. That's not exactly what I want. Okay, so, okay, but whatever. Okay, so hopefully you can see this. Okay, so I'm not sure if Zoom is covering anything up. It's covering it up for me, so hopefully you're not seeing this. So as you see after the first iteration, the first 2 elements are 10 and 2. Well, the first iteration just, sorts 10 and 2. You get 2 and 10. Third iteration sorts 10, 2, and 78. And then the first iteration sorts 10 and 2. The second iteration sorts 2, 10, and 78. The third iteration sorts the first 4 are 10, 2, 7, 8, and 4. So after the third iteration, the first 4 of the original array are in sorted order. Okay, so then after iteration 4, the first 5 of the original array are in sorted order. So to actually predict the output from iteration, or what's actually stored in the array from iteration is really not that bad. And I'd say the hardest thing is just this inner loop right here. And I would try to understand this. That inner loop. And then of course I have the same thing for, right? So for array of objects, I use the compare to method again. But really it's very minor changes to sort an array, to go from sorting an array of integers to sorting an array of objects. There's only 2 lines that need changing. So I'm going to stop sharing unless there's any questions. Okay, let's just finish the slides, students. I'm just talking about the complexity. Okay, so this was, okay. Okay, the thing, what I didn't share this, sorry, students. Okay, so now we should be able to see the slide. So this is where we left off. The thing that's interesting about, so the one thing about selection sort, it's always n-1 iterations. Every iteration is exactly one exchange after the inner loop. And the inner loop always calculates n minus, the number of iterations is always, well, it's from I to n-1. So it's, so, but there's always, it's predictable. Okay, so when I is 0, it's n-1 comparisons. Let me start again. We're doing selection sort. We start by going through the whole range, trying to find the absolute smallest from positions 1 through n-1. So the first iteration of selection sort does n-1 comparisons, and then after we find the absolute smallest, we do one exchange. And then it's n-2 comparisons and then one exchange. Okay, so it's always, so for an array of size n, I don't care if the array is actually sorted. So you might have this sorted array, you pass it to selection sort, it's still going to do all those, the exact same number of comparisons and the exact same number of exchanges. So the only thing that's important for selection sort is the size of the array. That part of it might be sorted or all of it might be sorted is irrelevant. It's always the exact same number of comparisons and exchanges for selection sort. So it's always, it always grows like n squared. Whereas insertion sort is a little bit different. Okay, so the number of you're always doing at least n-1 comparisons, right? You're always looking one to, because remember what you're doing is you're moving values to the left. And you're trying to see, oh, is the neighbor next to you greater than you do an exchange. So there's always at least one comparison. There's always n-1 comparison. So, I want to see if position 1 is in its, the element of position 1 is in its proper place. Like see here that for like that, I want to put 78 in its proper place. So I compare 78 and 10. One comparison, 78 is not less than 10, so we stop. But we had to still do at least one comparison. So to put any element in its proper place for insertion sort, there's at least one comparison. Now, if the whole thing was sorted, there'd be exactly n-1 comparison. So for an array that's sorted or close to sorted, you're only doing n-1 comparisons for insertion sort. And then 0 exchanges. So for an array that's already sorted, you're doing 0 exchanges. Okay. Let's go back to that next. Let's look at the best case scenario. So if you have a sorted array, like I have that example there, 9, 11, 23, 44, and 80. Oh, I want to put 11 in its proper place. 11 is greater than 9. Oh, stop. Now let's put 23 in its proper place. Oh, 23 is greater than 11. Stop. No exchanges. Okay, now let's put 44 in its proper place. 44 is greater than 23, so we stop and we go on to 80. 80 is greater than 44. So there's actually no exchanges. So in this case, for this array, there'd be 4 comparisons and no exchanges. So it's linear, right? So so in this case, it grows like the number of operations is about n. So if the array is close to sorted, insertion sort, doesn't really grow very fast. Okay, but the bad thing is, let's say you're trying to sort in ascending order, like from smallest to largest, and it's actually descending. Let's say it's a real mess, like this one right here. Oh, this is descending. 19, 13, 8. Yeah, we start from biggest to smallest. Okay, and so so you're going to do all these. You're going to do lots of comparisons, and so the inner loop. In each iteration, the inner loop is going to do I-1 comparisons and I-1 exchanges. And so remember that formula 1 plus 2. So there's always I-1 comparisons for like this really bad case right here. and so we're trying to sort a descending array with insertion sort. So remember, it's always, how many compares? So now is one, it's one exchange and one comparison, then +2, +3, and then plus. So for each iteration, that's the number of exchanges and comparisons. And that's actually, if you sum that up, if you remember, that's going to be n. Actually, yes, I think they go n minus 1. So that's order n squared. So insertion sort has like this best case and worst case property. So, and again, you wouldn't really use insertion sort or selection sort in a very large array because it's still, even in the best case, it's growing like n. There's another algorithm called, two other algorithms called quick sort and merge sort, which grows like log of n. Okay, so we'll talk about those. And they're at least quick sort is recursive. So students, that's all. I'm going to stop sharing. And I feel like I talked a lot. I did put up here. Let me just share this one. I'm not sure I'm going to. We've already done a couple of problems either in the slides or the maybe in the computer program. I do have. Look at. I did put this worksheet up there. So we'll talk about this next time. I'll put the solution file up there. Can I move this? Why can't I move this? Well, hopefully you're seeing the worksheet. That's what I was intending to share. And yeah, so you're just going to write out so basically you're going to do what I just did. Write out the state for all these exercises. You're going to show you're going to show the state of the array for every iteration. And I do have one really fun problem. Oh, I have a typo. I'll have to fix that. For problems, the last two, we're going to sort an array of strings, but I'm saying it's that string 1 will be less or greater than string 2. We're not going to look at the contents. We're going to look at the length. And the bigger the length, the bigger the string. And you can still sort. So we're going to sort by using that criteria. And right, so if you actually write the comparable method so that it orders by length and not by location in the dictionary, yeah, it would work. So I'm going to stop sharing this. Now, yeah, we'll talk about this next time. And next time we'll also talk about the famous shell sort algorithm, which is just a variation of insertion sort. In case students, just to, so just, I know you're probably in a lot of suspense right now. There's nobody there. So shell sort is not based, it's not like shells. It's not like the kind of shells, maybe if you like took calculus, you did the shell method, or you go to the beach, there's shell. It's not like that. There's a computer scientist named Shell, and he developed it. So I think it's like the most famous thing he did. This guy Shell, he developed this algorithm called shell sort. For years, I just thought it had to do with shells, and then, no, there's a computer scientist called Shell. Okay, so, oh, my light went on by magic. Yeah. Okay, so students, I'm going to stay here until there are any questions. I think there's a quiz due today. Is that right? I forgot. Check. I put an announcement in. I think it's easy if there is. And I shouldn't say that. What if you really bomb it? I'm saying it's easy. Yeah, I'm not supposed to. Just remember, students, easy is what you know and hard is what you don't know. And if you do bad on the quiz, I think everyone's capable of getting an A. But if you do really bad on the quiz, all that means is you have a growth opportunity ahead of you. It doesn't mean that doesn't mean anything bad. Okay, so this means, why is it, I thought I had my computer plugged in. I guess I still have plenty of time. I'm not about to lose power. But are there any questions right now, students? Otherwise, I'm just going to stay here until there are no more questions. And I think I'll stop recording.